Hello, my name is Allison Harvey, and this video is going to focus on how we can use Riemann sums, specifically the midpoint rule, to find the area or approximate the area under a curve. So, just reiterating some facts about Riemann sums is that we can approximate the area under a curve by either using left endpoints, right endpoints, midpoints, etc. And this video is specifically going to focus on the midpoint rule. So starting off with an example, say that we are given the function y equals x squared, and we are confined on the interval 0 to 8, and we are told that we can use 4 rectangles and that they would like for us to use the midpoint rule. So the first thing that I always like to do is I like to find delta x, and delta x equals b minus a over n. Delta x is going to tell me the width of my rectangles so that I know how I can separate out my interval. So to do that, b is 8 for this specific function and a is 0. So I do 8 minus 0 divided by 4 because n is the number of rectangles and they told us that they want us to use 4 rectangles. So 8 divided by 4 equals 2. So the width or the length of my interval is going to be 2. So I come down here and I sectioned off my interval. I did 0, 2, 4, 6, 8. Now, they want us to use the midpoint rule. So I'm going to find the midpoint in between each section. So that is 1, 3, 5, and 7. To approximate the area using midpoint rule, I am going to multiply delta x by the sum of these functional values at these midpoints. So the area can be determined by multiplying delta x by the sum of the function's values at these midpoint values. So that is going to equal 2 times f of 1 plus f of 3 plus f of 5 plus f of 7. F of 1 is 1, f of 3 is 9, f of 5 is 25, and f of 7 is 49 because our function is x squared, so I'm just squaring all these x terms. So that becomes 1 plus 9 plus 25 plus 49, which equals 84. And 2 times 84 is 168. So this isn't the exact area, but this is an approximation of the area using midpoint rule. And visually, how that looks is I've separated my graph into my sections and my rectangles, and I'm going to have a midpoint here. So it's midpoint, rectangle, midpoint in the middle of the rectangle, as you can see. And this is only a partial part of x squared. I just am showing you that interval. So again, the answer for this question is 168. We have another example. Say that we're given the function f of x equals x cubed, and we are on the interval 0 to 10. They want us to use 5 rectangles because I know that n represents the number of rectangles, so n equals 5. And just a reminder that delta x equals b minus a over n. So the first thing we're going to do is calculate delta x. So delta x is going to be 10 minus 0 because b is 10 and a is 0, divided by 5 because 5 is my number of rectangles. So 10 minus 0 divided by 5 equals 2. Again, the width of my partitions or subintervals, if you will, the rectangles is going to be 2. So I make a number line, and I know that I'm on the interval 0 to 10. Now I'm going to go up by lengths of 2. So I go 0, 2, 4, 6, 8. Again, we're using the midpoint rule, so I'm going to find the midpoint of each interval. So the midpoint from 0 to 2 is 1. The midpoint from 2 to 4 is 3. Midpoint from 4 to 6 is 5. 6 to 8 is 7. And 8 to 10 is 9. Again, we can approximate the area using midpoint rule by multiplying delta x by the sum of the function evaluated at these midpoints. So that is going to equal 2 excuse me, times the function evaluated at 1 plus the function evaluated at 3 plus the function evaluated at 5 plus the function evaluated at 7 plus the function evaluated at 9. The function evaluated at 1 is 1. Again, we're cubing these x values because the function is f of x equals x cubed. Function evaluated at 3 is 27, 5 is 125, 7 is 343, and 9 is 729. I added up all these terms, and that comes out to 1,225 times 2, which equals 2,450. So This isn't the exact area, but the approximation using midpoint rule for this problem is 2,450, and just visually, here's my graph.